Hello, and welcome to G Fun Facts Online, your go-to channel for diving deep into the fascinating world around us. Today, we're tackling a topic that's been a mathematical Everest for millennia: polynomial equations. You know those expressions like ax squared plus b, x plus c equals 0? They might sound like high school nightmares to some, but they're the secret sauce describing everything from a planet's orbit to the algorithms in your smartphone. The hunt for their solutions, or roots, is one of math's oldest and most thrilling adventures. Our journey starts way back, in ancient Egypt and Babylon. They had figured out how to solve simple linear and quadratic equations. That quadratic formula we all learn? Its roots stretch back thousands of years, with brilliant mathematicians like Abu Bakr al-Karaji in 1000 AD refining algebraic methods. Fast forward to the 15th century, and algebraic notation starts to look more like what we see today, moving away from just words to describe equations. The 16th century was a golden age for polynomial solvers. Italian mathematicians Scipione del Ferro, Niccolò Tartaglia, and Girolamo Cardano finally cracked the code for cubic or third-degree equations. Cardano even published these findings in his epic book, Ars Magna, in 1545. Not long after, his student, Lodovico Ferrari, figured out a method for quartic or fourth-degree equations, cleverly making it depend on solving a cubic. These were complex, sure, but they were general formulas using arithmetic and radicals, like square roots and cube roots. With cubics and quartics conquered, everyone thought quintics or fifth-degree equations would be next. But they hit a wall. A big one. For centuries, the brightest minds tried and failed. Then, in 1824, Niels Henrik Abel, building on Paolo Ruffini's work, dropped a bombshell: the Abel-Ruffini theorem. It proved there's no general formula, using only arithmetic and radicals to solve polynomial equations of degree 5 or higher. This didn't mean monomial quintic could be solved that way. X to the power of 5 minus 1 equals 0 is an easy one, but no single formula could do it for asterisk all of them. Mind blown. But why? Why this sudden stop at degree 5? The answer came from a young, tragic genius, Évariste Galois, in the early 1830s. Just before his untimely death in a duel, Galois laid down the foundations of what we now call Galois theory. This was revolutionary. He connected an equation's solvability by radicals to the structure of a special group associated with its roots, the Galois group. If this group was solvable, then the equation was solvable by radicals. Galois showed that the general quintic equation has a Galois group, called the symmetric group S, which is not solvable. And just like that, he explained the why behind Abel and Ruffini's theorem. It was a complete game-changer for understanding equations. So no neat formulas for higher-degree polynomials. But science and engineering still needed to solve them. This pushed mathematicians to develop powerful numerical methods. Think of techniques like Newton's method, the Lemmershur algorithm, or the Durand-Kerner method. These don't give you a pretty symbolic formula, but they can find approximate roots to incredible accuracy. And with modern computers, algorithms like the Jenkins-Traub algorithm can find all roots of a polynomial super efficiently. Computer algebra systems can even tell if a polynomial is solvable by radicals and spit out the solution, though for high degrees, these formulas can be monstrously huge. But the quest for new algebraic ways to solve these beasts didn't stop. And now, folks, there's been a really exciting development, potentially a new dawn. Mathematician Norman Wildberger and his collaborators have recently proposed a novel approach, detailed in publications around early 2025, to tackle higher-degree polynomials, including quintics, without relying on radicals in the traditional sense. So what's the big deal here? First, this new method tries to avoid irrational numbers, like the square root of 2, which often pop up in radical solutions and can be tricky for exact representation because of their infinite decimal expansions. Instead, it aims for solutions within rational numbers or as precisely defined series. Second, it uses power series, those infinite sums of terms, to represent solutions. You can truncate these series for great approximations, but the series themselves can be seen as a new kind of exact solution. And here's where it gets really cool. The coefficients in these power series come from hypercatalan numbers, which are multi-dimensional versions of the famous Catalan numbers you see in all sorts of counting problems. The researchers have even identified an underlying structure they've dubbed the geode, a novel array of numbers that seems to organize these hypercatalan sequences and is key to their solution method. Wildberger suggests this could be a dramatic revision of a basic chapter in algebra. Importantly, this isn't about contradicting Galois theory. Galois theory tells us about solvability, tangent by radicals. This new method is an alternative path, a different way to express solutions. They've even used it on historical equations and found connections to earlier work on series solutions. And the innovation doesn't stop there. We're seeing advances in computational Galois theory, making it possible to calculate Galois groups for much higher degree polynomials than ever before. There's also super interesting work in neuro-symbolic AI, where machine learning and symbolic math team up. Imagine AI models that can classify Galois groups by looking at patterns in roots. And, of course, numerical root-finding algorithms are constantly being refined to be faster and more robust, especially for really tough polynomials. The journey to solve these ancient mathematical puzzles has been an incredible engine for innovation. From ancient formulas to the deep insights of Galois, and now to these groundbreaking series-based solutions, the story of polynomials is still being written. These new methods aren't just about powerful new tools. They deepen our awe for the beauty and the ever-evolving nature of algebra itself. Thanks for tuning in to G Fun Facts Online. Join us next time as we explore another amazing corner of science and discovery. Until then, stay curious.